So far we have been discussing conservation equations and solutions of those equations for unidirectional transport, where transport is the variation of temperature, velocity or concentration is only in one direction. In both a Cartesian coordinate system, where the boundaries are planar surfaces, as well as in curvilinear coordinate systems. In those cases, there are as we saw, two effects. One is the unsteady part, the change in concentration or temperature with respect to time. Then there is a diffusive flux proportional to surface area, and then there is a source or sink which is proportional to the volume. And the mechanism of transport is only due to diffusion. Where you have velocity as well, there could be a mechanism due to convection as well. Okay. In momentum transfer alone, there could be transport of momentum by what is called a pressure. Okay. A pressure variation can generate a velocity field. This is different from both mass and energy conservation. In both of those cases, the quantity being transported is a scalar, temperature or concentration. It has magnitude but no direction. The flux was a vector, which is the direction of transport. In momentum, the quantity being transported is a vector, the velocity or the momentum. It has both magnitude and direction, and we had considered the mechanism of transport as the stress due to diffusion. Okay. The stress, if you recall, was the force per unit area acting at a surface whose outward unit normal is specified. Okay. That force acted parallel to the surface. Okay. That was what was called the shear stress. The pressure is a force that acts perpendicular to the surface. Okay. So, in this lecture we will start our discussion of pressure driven flow. Okay. So, pressure is a force, is a compressive force. Okay. It acts in the direction perpendicular to the surface along the inward perpendicular to the surface, and it tends to compress the differential volume. Okay. It tends to compress the differential volume. Even pressure exists even in the absence of flow. Okay. The shear stress was given by Newton's law for viscosity, which was tau x z is equal to mu dvx by dz if velocity is only, if the x velocity is a function of z. So, this exists only when there is flow. Okay. The pressure, on the other hand, is a force per unit area which exists even in the absence of flow. Okay. So, even in hydrostatic conditions, if you had a certain level of water, okay, in a tank, you know that, for example, Bernoulli's law states that pressure is equal to rho g into h. This pressure acts on the bottom surface. It also acts on the surfaces on the side. Okay. It tends to act in perpendicular to the surface. Okay. It tends to act perpendicular to the surface. The pressure also acts on a differential volume within the fluid. Okay. Pressure also acts on a differential volume within the fluid. Okay. Within this fluid, the pressure acts along the compressional axis. Okay. It tends to compress the volume. Okay. Okay. So, it acts along the inward unit normal. Okay. The pressure acts along the inward unit normal, and it tends to compress the volume. Okay. That is why it is called pressure. Note that the stress we had defined with respect to the outward unit normal. So, the pressure is actually the negative of the stress perpendicular to the surface. Now, the definition of pressure could be in one of two ways. Okay. One is what is called the thermodynamic pressure. Okay. The thermodynamic pressure for example, given by the ideal gas law, P is equal to n kBT if you express n as the number of molecules per unit volume, or n RT if you express it as the number of moles per unit volume, where T is the absolute temperature. Okay. So, this is what is called an absolute pressure. Okay. It is a thermodynamic pressure. Okay. And this is 0 at absolute when the temperature is at absolute 0, and then it increases. Okay. Of course, there are corrections to this ideal gas law when the density of the gas becomes large, and similarly for liquids and so on. Okay. But this is an absolute pressure. Okay. The dynamical pressure, on the other hand, is often is a relative pressure. Okay. For example, when we measure a pressure, for example, under terrestrial conditions, it is always with respect to the atmospheric pressure. So, there is a constant background pressure, which is the atmospheric pressure. Variations in pressure about that, okay, positive or negative, okay, can cause fluid flow. Okay. So, this pressure that we encounter relative to the atmospheric pressure can be both positive or negative. Okay. So, for example, in the atmosphere, you will have some regions which are lower than atmospheric pressure and some regions that are higher than atmospheric pressure, and this difference in pressure is what will generate flow. So, flow is generated by pressure variations, okay, by differences in pressure, okay, not by the background absolute pressure itself. Okay. And that is the dynamical pressure. Okay. The dynamical pressure is defined only relative to a constant background value. Okay. The dynamical pressure is defined only relative to a constant background value, and if you add a constant to that pressure, the velocities will not change because the pressure variations do not change. Okay. So, if you have a pressure field which is generating a certain flow, incompressible flow, okay, so we assume that the density is a constant, and so the pressure field is generating an incompressible flow. If you add a constant pressure everywhere, okay, in the equations of motion, the velocity field will not change because the velocity depends only upon variations in pressure. Okay. So, in that sense, this dynamical pressure is defined to only within a reference level. Okay. You can add a constant value or subtract a constant value everywhere from the pressure field, and the velocity will not change. In contrast, the thermodynamic pressure is an absolute pressure. It cannot be negative, okay, because the temperature is necessarily positive. Okay. So, thermodynamic pressure is an absolute pressure, whereas the dynamical pressure, you should remember, is primarily, or it should be interpreted as a pressure difference or a pressure variation. Okay. In general, a background pressure will be subtracted from this. Okay. And for example, in most cases that is the atmospheric pressure. Okay. So, dynamical pressure is what generates flow, or rather dynamical pressure variations generate flow. Okay. So, there is a difference between thermodynamic pressure and the dynamical pressure. Okay. Okay. The dynamical pressure is defined only to within an unknown constant. Okay. With that, so pressure is of course force per unit area acting perpendicular to the surface. So, with that, let us start our discussion of laminar flow in a pipe. Okay. We will calculate the momentum conservation equation when there are pressure variations. Okay. This is probably the most utilized unit operations in industries, okay, in order to transport fluids. Okay. Pipe, okay, of radius r, okay, distance x along the axis, and I will use a cylindrical coordinate system where r is the distance from the center. Okay. And in this case, due to the applied pressure difference across the ends, okay, there will be a velocity profile, okay, due to the applied pressure difference across the ends of the pipe. And we will get an equation for the momentum balance in the x direction, okay, balance equation for the x momentum by considering a differential volume bounded by surfaces of constant coordinate. Okay. So, in the radial direction, the surfaces are at r and r plus delta r, separated by infinitesimal distance delta r. In the axial direction, the surfaces are at x and x plus delta x, separated by an infinitesimal distance delta x. Okay. Okay. So, that is how that differential volume would look. I will expand it out so that it is easier to visualize. Okay. So, this inner is at radius r, the outer is at r plus delta r, okay. The left side is at x, the right side is at x plus delta x. Okay. And we are writing an equation for the axial momentum. Okay. The momentum conservation equation, if you recall, is rate of change of momentum is equal to rate of momentum in minus rate of momentum out plus sum of forces. Okay. Okay. So, there are 4 surfaces. Okay. There is a surface at r, surface at r plus delta r, surface at x, and surface at x plus delta x. Okay. And each of these have their own surface areas. Okay. Okay. So, the surface areas, okay, the surface at r is going to be equal to, this is the curved surface area at r, it is going to be equal to 2 pi r, okay, into delta x. Okay. 2 pi r is the perimeter of the circle times delta x is the length. Okay. This is the surface area of the cylindrical surface. Okay. Surface at r plus delta r is equal to 2 pi into r plus delta r into delta x. Okay. Surface at x, okay, the surface area, okay, the surface at x is the disk between the two circles at r and r plus delta r. Okay. So, this is going to be equal to the perimeter times the thickness. Okay, it is going to be equal to the perimeter times the thickness, and similarly the surface at x plus delta x is going to be the same thing. The perimeter times the thickness, that is the disk between r and r plus delta r, okay, the annular region between r and r plus delta r. And the volume is equal to 2 pi r delta r, the thickness times the length along the x direction. Okay, so First we will look at what are the forces. Okay. The rate of change of momentum. Okay. Okay, is going to be the change in the density divided as change in the momentum density times the volume. Okay. Change in momentum density is delta of rho Vx, okay, by delta t. The rate of change of momentum in a time interval delta t is going to be equal to rho Vx at t plus delta t minus rho Vx at t divided by delta t. That is change in momentum density multiplied by the volume 2 pi r delta x. Now, what are the forces acting on the surface? Okay. There is a force that is exerted on the surface at r plus delta r. Okay. There is a force exerted on the surface at r plus delta r. Okay. Note that tau xr is the stress, is the force per unit area in the x direction at a surface with outward unit normal in the r direction. Okay. At a surface with outward unit normal in the r direction. Okay. At the surface at r plus delta r, the outward unit normal is in the r direction. Okay. So, therefore, the force here is tau xr at r plus delta r, okay, into the surface area, that is 2 pi into r plus delta r into delta x. Okay. That is the force exerted on the surface at r plus delta r. Okay. Okay. So, therefore, force on surface at r plus delta r in the x direction is equal to tau x r at r plus delta r into the radius is r plus delta r. Okay, 2 pi into r plus delta r into delta x. On the surface at r, the unit normal is in the minus r direction. Okay. On the surface at r, the unit normal is in the minus r direction. Therefore, the stress on the surface at r is minus tau x r, okay, into 2 pi r delta x. Okay. Because the unit normal is in the minus x direction, therefore, the force is minus tau x r, okay, because when you interchange the sign of the unit normal, that the sign of the force also changes. Okay. If you recall, that was from Newton's law, that if you have a particular surface, if you have a surface and the volume above exerts a particular force in this direction on the volume below, the volume below exerts an equal and opposite force on the volume above. For the volume below, unit normal is this way. So, therefore, with an outward unit normal is in the plus x direction, if you have a force in the plus x direction, for the volume above, the unit normal is in the opposite direction. Okay. So, the force is opposite. Okay. So, force on surface at r is equal to tau x r at r into 2 pi r delta x. Okay. So, there is a force on the surface at r in the x direction. Okay. The pressure at these two surfaces acts perpendicular to the surface. So, that pressure is actually in the radial direction. Okay. So, it will not come into the axial momentum conservation equation. The pressure is in the x direction on these two surfaces. You have pressure that is acting in the x direction. It is compressive. Okay. Okay. It is compressive. Therefore, on the surface at the left it is acting in the plus x direction, on the surface at the right it is acting in the minus x direction. Okay. Therefore, the force on surface at x is equal to plus the pressure at x, right, the pressure at x times 2 pi r delta r, which was the surface area of that surface, okay, between r and r plus delta r, okay, the disk between r and r plus delta r. Okay. On the right face the pressure is acting inwards, which means that it is acting along the minus x direction. Okay. On the right face it is acting inward, which means that it is acting along the minus x direction. Okay. Is equal to the pressure at x plus, it is acting in the minus x direction. So, it is minus the pressure at x plus delta x 2 pi r delta r. Okay. And finally, there is a momentum flux. Okay. The flux of x momentum on the left face because fluid is entering, the flux of x momentum on the right face because fluid is leaving. Okay. So, on the left face fluid is entering the volume and therefore, momentum is entering that volume. On the right face the fluid is leaving and therefore, the momentum is leaving that volume. Okay. So, rate of momentum in, note that there is no velocity around the cylindrical surfaces, there is no flux of momentum there. Okay. So, rate of momentum in okay, at x okay, is equal to the momentum density times the velocity times the surface area. Okay. The momentum density times the velocity times the surface area, okay, of the left face. Okay. Note that the flux is a density times the perpendicular velocity, okay, and the rate in is flux times area. Okay. So, density in this case is rho v x, the velocity is v x, and then you have the surface area. Okay. Rate of momentum out at x plus delta x is equal to rho v x into v x into 2 pi r delta r. Okay. Note that this is at the location x, this is at the location x plus delta x. Okay. So, those are the rates of momentum in and out and the forces. Okay. So, we will substitute this into the balance condition. Okay. Substitute this into the balance condition. Okay. The term on the left is the delta of rho v x by delta t 2 pi r delta x, rate of change of momentum is equal to momentum in minus momentum out. Okay. Momentum in and momentum out have the same areas, okay, rho v x square at x minus rho v x square at x plus delta x, okay, plus the force on the surface at r plus delta r, tau x r at r plus delta r 2 pi into r plus delta r, okay, into delta x. Force on the surface at r, that you recall was in the negative direction, okay, that you recall was in the negative direction, okay, as I had said. At this surface the force is acting in the negative direction because the unit normal is in the opposite direction. Okay. So kindly note that the force acting at the surface at r, because the outward unit normal is in the minus r direction, the force is minus tau x r. Okay. So, into 2 pi r delta x. Okay. plus the pressure. Okay. Pressure in the plus x direction at the surface at x. Okay. So, P at x into 2 pi r delta r, okay, minus P at x plus delta x into 2 pi r delta r. Now, we will restrict our attention to what are called fully developed flows, that is the velocity does not vary in the x direction. Okay. This is not a steady flow. Steady flow means velocity does not vary with time. A fully developed flow means velocity does not vary with axial position. Okay. It could vary with time, but at each instant of time it does not vary with the axial position. Okay. So, you the volume coming in on the left has to be equal to the volume going out on the right. Okay. That is a requirement for an incompressible flow, okay, because you know that mass coming in and mass going out have to be same. If the density is also a constant, then the volume coming in and volume going out has to be the same. In that case, the velocities have to be the same. Okay. And for a fully developed flow, okay, it could be a function of time, the velocity, but it is not a function of the downstream location. Okay. In that case, the velocity at x and x plus delta x will cancel out. Okay. And in the remainder of the equation, I divide throughout by the volume. Okay. 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 I cancel out x and x plus delta x. So, divide by 2 pi r delta r delta x. Okay. And I will get the change in rho v x by partial t is equal to, okay. Note that in these two terms the surface area is changing. Okay. In these two terms the surface area is changing. The outer and inner cylinders, the surface area depends upon the radius. So, you have different surface areas. Okay. Therefore, this becomes 1 by r delta r into tau x r into r. Okay. Sorry. Minus tau x r at r into r. Okay. The stress at the outer surface times the radius minus the stress at the inner surface times the radius. Okay. Plus, okay, 1 over delta x. Okay. Note that these two terms do not have a delta x in them. Okay. So, therefore, when I divide by delta x, I get a 1 over delta x into p at the location x minus p at the location x plus delta x. Take the limit delta t, delta x, delta r all go to 0. Okay. I will get partial of rho v x by partial t is equal to 1 by r d by dr of r tau x r minus partial p by partial x. Okay. For an incompressible flow, the density is a constant and I will get rho partial v x by partial t. Newton's law for viscosity, tau x r is equal to mu partial v x by partial r. And if the viscosity is also a constant, then you can take it out. So, this is the momentum conservation equation for a pressure driven flow, and the other additional term here is the pressure variation in the x direction. Okay. So, this is the additional term that appears for a laminar flow when there is a pressure gradient. I will continue this discussion in the next lecture. We will solve for the laminar profile and from that the correlation for the friction factor for a laminar flow. I will continue this in the next lecture. I will see you then.